Hello, everybody. Welcome to Astronomy 5, Week 9, and kind of getting the hang of making these recordings. I have not figured out how to use my camera on my MacBook yet. That might happen here. All right. Hope you're all doing well, and pay attention to what's due this week. Everything is posted. If you don't see something posted, then please send me a message. Everything is on Canvas for what's due, and Mastering Astronomy is still the website for the homework. Things we're going to be talking about will piggyback off of last week's lecture, and hopefully you find it fascinating. This is some really interesting stuff here in astronomy, and it lays the groundwork for why we think what we know. This guy is Ejnar Hertzsprung from the famous Hertzsprung-Russell diagram. I love the picture, it cracks me up. So Ejnar Hertzsprung's father had studied astronomy, but he wasn't an astronomer. He earned his living as an insurance executive. The son, Ejnar Hertzsprung, was fascinated with his father's charts of the heavens, and he didn't want a career in insurance himself. He studied as a chemist. He wanted to be an astronomer, and also realized that he didn't also want to be poor, because astronomers, were either really well-to-do or they were really poor. He briefly worked in Wilhelm Ostwald's laboratory, and in 1902, while he was still working as a chemist, he began volunteering at Urania Observatory in Copenhagen. In 1905, he published his first paper on astronomy, proposing a relationship between the spectrum and luminosity of stars. So, okay, let's break in for a sec. What is luminosity? And we talked about this on the last week short lecture. It is the amount of energy an object emits. So he finally switched careers in 1909, giving up chemistry to accept Karl Schwarzschild's offer to lecture in astronomy at Göttingen. And Schwarzschild, the name, just put it in the back of your mind. So, because Karl Schwarzschild, as a little off thing here, he was a physicist and astronomer, and he developed the concept of black holes, showing that when stars undergo gravitational collapse and shrink below a certain size, what's now called the Schwarzschild, I can never say that right, Schwarzschild radius, the gravitational pull becomes so great that not even light can escape. In essence, the radius of a collapsing celestial object at which gravitational forces require an escape velocity, remember escape velocity? What it takes to get out of the orbit of an object, that exceeds the velocity of light, results in a black hole. So if the escape velocity is faster than the speed of light, you've got a black hole. So as early as 1906, our buddy here, Hertzsprung, plotted the absolute magnitude of stars in relation to their luminosity, classification, and effective temperature. In 1910, he met with American astronomer Henry Norris Russell, also the chart now called the Hertzsprung-Russell diagram, who had reached very similar conclusions independently, and the two astronomers merged their results in, again, what we call the Hertzsprung-Russell or HR diagram, published in 1913, which remains today a cornerstone of modern astrophysics. Hertzsprung also developed a vastly improved method to determine the relative positions of the components of double stars, and published important papers on the evolution of open star clusters and variable stars. He spent 25 years at the Leiden Observatory, the last 9 years as director, and was among the last self-taught astronomers to oversee a major observatory. Kind of a cool dude. Look at this cover of Life magazine, and I'm going to sound sarcastic for a second because this was a cover from when Americans valued intellect. And people with an intellect made the cover of Life magazine. Henry Norris Russell. If the measure of the values and intellect of a society is based upon media, we're in trouble. So, Kanye West, Kardashians, just saying. Henry Norris Russell was for many years the leading theoretical astronomer in America. He graduated from Princeton in 1897 at the age of 19. His father, interestingly, was a Presbyterian minister, and his mother and maternal grandmother both won prizes in mathematics. The apple doesn't fall far from the tree. He recalled in later detail his parents showing him the transit of Venus in 1882 when he was just 5 years old. In 1905, he was appointed instructor in astronomy by Woodrow Wilson, the president at the time. Russell pioneered in the use of atomic physics for the analysis of the stars and thus played a very principal part in laying the foundations of present-day astrophysics. He analyzed the physical conditions and chemical compositions of stellar atmospheres and evaluated the relative abundance of the elements. His assertion of the overwhelming abundance of hydrogen in our universe was accepted after very prolonged controversy as one of the basic facts of cosmology. And when we talk about astronomy being, hydrogen as a basic fact of cosmology, we're talking about background hydrogen from the theory of the Big Bang. So, this semester up until this point, we've been building the foundation by which we view the universe today. Everything we've done has culminated in being able to classify stars on this HR diagram. Really, that's the culmination of ancient to modern astronomy. It's not astronomy in its entirety, but it's definitely a huge undertaking just to get these stars onto this diagram and breaking apart the components of physics, chemistry, basically all of science goes into being able to put stars on this really simple diagram. And you'll look at it in your textbook and you'll say, well, that's really basic. But it's not, getting them there wasn't a basic undertaking. It's really a culmination of so much science. So what we've discussed in this class has led us right to the doorstep of this chart. Yet we really don't know, because everything in astronomy is built on this idea that the premise that it's built on previously withstands theoretical testing. And every theory in astronomy is built on the backs of other theories. And so I want to say it's a house of cards, but it definitely changes things if something is disproven. So just a little thought, because we're all scientists here and we're all learning about astronomy. And I want you guys to take what we say as fact, but also take it as a theory that can be undone if it doesn't withstand testing. And what I mean by that is that, yeah, we see the sun spectra, and we discussed Fraunhofer and Fraunhofer lines. We've observed spectral lines in the laboratory and noticed they are the same as the elements that we view on the Earth. When we look at hydrogen burning and the spectral line of hydrogen, and we look at black body radiation. We know, we can look at the inverse square law for light and the one for gravity, and we have these theories for speeds of light, theories for stellar formation, based on a lot of it comes from what we think our own solar system or how it formed, theories for how matter interacts under all kinds of conditions. And so we have all these pieces to a puzzle coinciding with the biggest mystery ever challenging human understanding, and that's really our understanding of our place in the universe. And we look at it from an entirely human perspective, from a single small point in space, the Earth. How does that hinder and color our perspective? Let's add to this that we humans live very cosmologically brief lifespans. What's the minimum life cycle of a star? 1,000,000 years? How long have humans been walking upright on the surface of this planet? Definitely not 1,000,000 years, right? We rely on a foundation of building knowledge upon the works of others to further our understanding of astronomy. And so think about how important it is to always challenge that base of knowledge that we build upon. And that's really what I want to throw out here with this slide talking about aliens. If we find a flaw, is it something that explains what we understand to a finer degree, or does that flaw put a crack in a foundation? It's an interesting thought. So here we are on the top right with this HR diagram, and you have it in your textbook, and it can be definitely seen a lot bigger in textbook, that our buddies Hertzsprung and Russell came up with. And what they deduced was that the spectra of stars was equivalent to their luminosities. That is, the hotter the star, the more the spectra shifts towards the blue end of the spectrum. The cooler, the more it shifts towards the red end. And if we know how far a star is away from us, we can figure out how much light we should see if the star was 10 parsecs away from us. Remember, absolute magnitude. Then we have temperature, spectral class, size, and based upon astrophysics, the lifespans of stars, all on this amazingly simplistic looking chart. And I do have these YouTube videos on here, and I'll try and post a bunch of links for things that I really wanted to show you in class, so don't fret. So remember when I showed you guys an image of the middle of our galaxy at the beginning of the class, the region of Sagittarius A star? The issue at the time I think we were discussing was accretion disks, or I was just kind of glossing over it. When stars are born, they develop from large clouds of molecular gas. This means that they form in groups or clusters, and since molecular clouds are composed of hundreds of solar masses of material, after the remnant gas is heated, it gets blown away. We weren't seeing that in the image I showed you guys. We did see a lot of gas and dust. Not sure what that means for our model of stellar formation. Anyhow, the newly formed stars collect together by gravity, and during the exchange of energy between the stars, some stars reach escape velocity from the protocluster and become runaway stars. The rest become gravitationally bound, meaning they will exist as a collection of orbiting each other, quote, quote, forever, end quote, When a cluster is young, the brightest members are O, B, and A stars, and your textbook does discuss this really well. Young clusters in our galaxy are called open clusters due to their loose appearance. They usually contain between 100 and 1,000 members. Early in the formation of our galaxy, very large globular clusters formed from giant molecular clouds. Each contain over 10,000 members. and they appear very compact and have the oldest stars in the universe as we see the universe now. And I'm kind of just throwing it out there. Since all of the stars in the cluster formed at the same time, they are all in the same or relatively same age. A very young cluster will have an HR diagram plotting with a cluster of what they call T Tauri stars evolving towards the main sequence. And take a look in your book and you'll see what I'm talking about. As time passes, the most massive stars at the top of the main sequence evolve into red giants. Therefore, the older the cluster, and this is where I'm going with this, might have sounded like I was kind of going off on a tangent. Therefore, the older the cluster, the fewer stars to be found at the top of the main sequence. The main sequence is what we consider to be where stars are born and their lifespan, where they kind of go to die. You'll see this whole HR diagram plots out the birth and death of stars. So the older the cluster, the fewer stars to be found at the top of the main sequence, with an obvious grouping of red giants will be seen at the top right of the HR diagram. So the effect of an evolving HR diagram with age becomes a powerful test of our stellar evolution models. We've built computer models that follow the changes in stars of varying masses over time, and we've built theoretical HR diagrams at each time step, and observations of star clusters are compared to these computer-generated HR diagrams to test our understanding of stellar physics. And guess what? Our testing seems to be pretty accurate. Look at this pretty picture here. M16, M as in Messier object from Charles Messier. Look at this. These are regions of new star formation from gaseous clouds of dust and other interstellar material. So like I said in the beginning of the semester, one of the things I wanted to lead you guys to, which you probably already knew, but I want to definitely expand this, is that we have these amazing images, and these amazing images tell you so much more than just being a pretty picture. Interstellar medium. So this is the region between the stars in a galaxy like the Milky Way. It's far from empty. These regions have very low densities. They would constitute a vacuum. However, they're really filled with gas dust, magnetic fields, charged particles. This is what the interstellar medium is and why we call it that. Approximately 99% of the mass of the interstellar medium is in the form of gas, with the remainder primarily in dust. Dust. Can't speak, a little dust in my nose. The total mass of the gas and the dust in the interstellar medium is about 15% of the total mass of visible matter in the Milky Way. Where's the other 85% of the matter? So of the gas in the Milky Way, 90% by mass is hydrogen. And that's what we were talking about, cosmology. Going back into the basic fundamental idea that hydrogen is one of the basics of cosmology when we were talking about Henry Norris Russell. The remainder of the gas is mostly helium. The gas appears primarily in two forms. Number one, cold clouds of atomic or molecular hydrogen, and number two, hot ionized hydrogen near hot young stars. The clouds of cold molecular and atomic hydrogen represent the raw material from which stars can be formed in the disk of a galaxy if they become gravitationally unstable and collapse. Remember, the cloud has to collapse on itself before you start having a larger gravitational pull towards a central mass. Although such clouds do not emit visible radiation, they can be detected by their radio frequency emission. Why radio frequency emission? Because it's cold gas, right? And remember what radio frequency emissions are. They're very long wavelength. Look at this beautiful slide. So ionized hydrogen is produced when the ultraviolet radiation emitted copiously by hot newly formed stars ionizes surrounding clouds of gas. The color red, which we consider like characteristically beautiful red color, is of emission nebulae, like what's called right here M42, remember Charles Messier again, the Orion Nebula, or the Trifid Nebula. These colors are produced by visible light emitted when the electrons recombine with the ionized hydrogen in these regions. Side note, what would make electrons recombine, or how could they recombine? By interacting with cooler material. Remember that it was the heat that caused the ionization. Such regions of ionized hydrogen are called H2 region, hydrogen 2 regions, while cold unionized hydrogen clouds are termed H1 regions, with the 1 and the 2 referring to the ionization state. Remember, ionization is of the electron, right? The disk and its spiral arms are heavily populated by both H1 and H2 regions. Okay, so interstellar dust grains are typically a fraction of a micron across, which is approximately the wavelength of blue light. They're irregularly shaped and composed of carbon and/or silicates. And what's silicate? Sand, right? Absorption of light by dust causes large dark regions. In our galaxy and in other galaxies, these dust clouds are visible if they absorb the light coming through them. We then refer to these clouds as dark nebulae, such as the Horsehead Nebula on the bottom, right below all of the writing, and you can see another picture of a dark nebula on the right. On the other side of this, rather than a dark nebula, we have light that can be reflected from clouds of dust and gas, and we call these, they look very beautiful, they're called reflection nebulae. So dust has two major effects on light passing through it. The light can be dimmed by the dust, and this dimming is called interstellar extinction. The light that does not, or that does pass through the dust is depleted in blue wavelengths because the size of the dust grains favor scattering blue light, right? Why do we see red sunsets? Blue light's scattered. Why does the sky look blue? Blue light scattered. This is called interstellar reddening when we're looking out into deep space, in interstellar space, because the resultant transmitted light is more red than it would have been otherwise because the blue light's scattered around. This implies that transmitted light will be more red, but reflected light will be more blue. Quantitative observations in astronomy must correct for both extinction and reddening of light by the interstellar medium. And continuing on with that, the Pleiades on the bottom right, it is an example of a reflection nebula. As you would expect, for star formation from interstellar medium to occur, there needs to be material that can stick together, accrete, as in the accretion process. The more material, the better. Just because there is materials available, though, doesn't mean that it is right for the taking. Gravitational equilibrium exists in gas clouds too. Most of the time, and don't forget gravitational equilibrium, we're talking about gravity versus the pressure, right? As in the bottom, in the battle of gravity versus pressure, if gravity wins, the cloud collapses into stars. So most of the time, the outward force in gas clouds keeps the accretion process from occurring. The force of gravity can be overcome if interstellar medium, the gas between stars, if it is dense enough, and if it's cold enough. What happens when things get hot? They radiate, and heat keeps gravity at bay to some degree, right? We need temperatures to be cold enough for hydrogen gas to be able to combine and form hydrogen molecules. Sounds familiar. Same thing as in our solar system formation theory. And this is right out of the model scientists or astronomers use to explain why our solar system formed with rocky planets close to the sun and gas giants further out. It won't form an ice, but will gain more mass by creating molecules of H2 at temperatures between 10 and 30 Kelvin. That's very cold. It's very cold, especially if you consider what 0 Kelvin represents. We're talking about the freezing of atoms in place. Look at this beautiful picture. This is the star-forming Tarantula Nebula. How big are these clouds? The equation on the previous slide shows that you will need a cloud hundreds to thousands of times larger than the stars that are being formed. See, take a look at this. This equation tells us a lot of what is theoretically necessary for a cloud to contract and form a star. On the right, what size star we want to make, followed by the temperature to the third power, n, is the gas number density. What I want you all to see is that temperature is cubed. Any slight increases in temperature increases the required critical mass for a gas cloud to contract. That's what this formula is telling us. What is the magic number we need to achieve in order to collapse down into a protostar? And again, I always kind of go back to the basics. Think about the accretion process from the gas cloud of our own solar system. What number do we need to achieve in order to collapse our own sun down into a protostar? And I'm just talking because I feel like I need to talk over the slides that I don't have anything written for. You guys can read the slides. I'm just going to keep on keeping on. Or this would be a great time to pause, maybe get a drink of water, wander around, circulate your legs. These are molecular clouds at different stages. The temperature of the image on the left is less than 100 Kelvin. Why? What happens to hydrogen gas at higher temperatures? It expands. If it expands, what happens to the gas in that molecular cloud? The second image shows lumpiness and random motions. Isolated pockets, clumps start to form. These individual clumps can form protostars. Notice when they're clumped, they are not all equidistant. Some are closer, some are further, and as more matter clumps, it begins to have a higher gravitational attraction, right? Third image, as it contracts, it grows warmer. This is the conservation of energy principle, potential energy to thermal energy. That's the principle that says energy can't be created or destroyed, just converted. The thermal radiation lets energy leave, the contracting regions, but contraction traps in heat that can't be radiated away and slows the contraction process. The dust around what is called a protostar is visible in infrared because infrared is thermally warm enough, or thermally warm even though it's not visible. Remember, I can't speak, that as it shrinks, it spins in order to conserve its angular momentum. It trades energies, size for spin. It's trading size for spin. This cloud will start to rotate uniformly. Again, just talking over slides. It's been an interesting couple weeks. I hope you guys are all doing well. Pausing for you to read. Read away while I talk. Shuffling papers. Awkward silence. And next slide. Okay, so protostellar magnetic fields. Take a look at this slide. This is interesting. And if you can see it, maybe you can't see it, if not, maybe take a look on the internet and look at this protostellar magnetic field that's going on. The magnetic field will slow the rotation of the protostar. And then we get into more interesting stuff. Protostellar jets. And again, you guys can read the slide. I just want to say that the density along the axis of rotation traps energy along that axis because that's where material is falling inwards under the collapse of gravity. Is it possible that there is so much pressure, heat, and matter that forming stellar regions have magnetic fields? Yes. Again, protostellar magnetic field. And this energy needs to escape somehow. This is a really cool image. I wish I had a better version of it. Jets are full of high-powered X-rays that travel for hundreds of light years in both directions. You can also see blobs of materials that were also carried away with the jets. You can see this. Look on the very far left and the far right of the image. These are pushed along by the protostellar winds generated by a magnetic field. And this protostar loses energy and materials and eventually will just be a star on its own. And the magnetic field and the losing of energy and materials also helps it slow the angular momentum's acceleration from contraction, if that makes sense. Again, another really cool picture of the jets from a protostellar disk. And look at the distance of the jet with the bottom reference of 1,000 AU. all I have to say for this is on the bottom line, the magic number is 10 million Kelvin. Magic number. Hear me shuffling papers? Just like in class. If you close your eyes, we're back in class right now. Okay, least massive stars. This is cool stuff. Again, reflecting back on the HR diagram, which is part of your textbook, and you guys probably have looked at it already, I hope. The stars that were near the bottom right were cool and red stars, right? These stars are the low mass M class stars. And what am I talking about, M class? Take a look at the HR diagram. It tells you everything you want to know. They take the longest to form because we need 10 million Kelvin for fusion. Magic number, 10 million Kelvin. And by longest to form, we're talking about 100 million years. The lower limit is 0.08 solar masses. And when we talk about the HR diagram, we're talking about comparing things to solar masses. So when you see that 0.08 with a capital M and a little small circle with a dot in the middle, that's the symbol for mass of the sun. It's less than the mass of the sun. The lower limit for fusion to occur is 0.08 solar masses. Anything below that will not achieve fusion. And if that occurs, we have what is considered to be a failed star, which is a brown dwarf. And then we can go the other direction. And what happens if we try to bend some laws and try and change things and add too much mass? And then we have something called degeneracy pressure. And it says it right here on the bottom, laws of quantum mechanics prohibit two electrons from occupying the same state in the same place. So in this slide, we're talking about interior pressure remains stable as temperatures rise and fall. The more pressure on the electrons, the faster they move to counteract contraction. This does not produce thermal heat, though. It just stabilizes a star. And we have the circles on the right represent brown dwarfs in the constellation of Orion. We observe that there are more low mass stars being formed in proportion to high mass stars. The ratio is 10 to 1, low mass stars to high mass stars. And they don't produce heat. We don't see them. So we have all of these stars being held together with degeneracy pressure that aren't producing heat. The electrons are just keeping the stars stable. And why do we see this proportion occurring? We think it's because high mass stars live shorter lives. When they disappear, when they go supernova, they explode, they seed their materials all over the place, not just in one spot. And considering what we talked about earlier in the semester, things like calcium, potassium, zinc, iron. All of those things are not formed on the Earth. They required supernovae to seed the universe with those materials. They aren't naturally occurring here. We don't have enough heat. So what we see is all these brown dwarfs, but we really don't see them. They're hard to spot because what's interesting about brown dwarfs, like this is a picture from Hubble, is that in normal stars, they have gravitational equilibrium, and that's thermal pressure, right? Heat. Brown dwarfs never get to that point. And I may have misspoke earlier talking about degeneracy pressure. Instead, brown dwarfs use quantum mechanics in the form of degeneracy pressure because they don't produce enough heat to stop a collapse. They radiate in infrared and eventually fade into obscurity. And when we talk about dark matter, could this be a form of dark matter? Because when these objects fade into obscurity, what do they become? So, last slide, last for this week, 150 solar masses. This is the high end of star formation. We think this is because the energy at their cores would force their outer layers away from the star, essentially a repulsion of materials. It'd be too massive to hold materials to the surface. It's just too big. So, just food for thought. I hope you guys are enjoying the reading on this chapter. This is one of my favorite chapters in the textbook. And again, don't forget to take a look at what's posted and just maintain going through Mastering Astronomy. And again, the same thing applies with Mastering Astronomy. If you get it all done for the semester, you're done. And then just check it on Canvas and do the Canvas as you go.